Hello, everyone. First off, I hope everyone is doing well. So, it appears for the rest of the course, the lectures will be online. So, I'm going to try out this format. Um, we've missed a week, so we are a little bit behind. So, I'll discuss some of the changes in that regard, but more so the changes are due to the new format that the course is in. So um, the tests, for example, are probably going to end up being multiple choice. I can't really test you on work anymore, which for the theoretical portion of the course is the most valuable part. So, one thing I've always felt that the computer aspect of the course, kind of more along the lines of what we might do on the homework, is more valuable to you really than the kind of brief introduction to some of the theory that we go over in the course, which I guess is nice, but as far as if you'd have to actually do anything, um, I feel that the online or the computer aspect is much more valuable. And so, given the new format, um, I will probably make a shift in the testing to be more geared toward the computer aspect of things. So, um, in a way, maybe it will be more helpful in learning some of the more applied, useful stuff than some of the uh, theory, which is nice, but I would say in this course, for a lot of the stuff, we don't really go over it to an extent that you fully understand it anyway. Okay, so with that spiel done, my plan is to cover the remainder of the material for the second test with this lecture. With Thursday's lecture, I plan to just do review. And then for next Tuesday, so of course we were supposed to have our test this lecture, that's changed. So for Tuesday the 31st, I plan on having the second test. So what that is probably going to look like is, of course, you will have everything at your disposal, right? Can't limit you really. Um, the test will probably open at a specific time, such as probably the beginning of class, and I might give you more than just an hour and 15 minutes. Okay. The questions will probably all be multiple choice and probably be geared more towards the computer component. So, for example, R. Um, so there will be a certain time limit though. So you won't just have unlimited time to just say not know anything and just go look everything up. Um, so even if I do give you more than enough time, I would say if you haven't practiced some of this stuff, um, as I'm sure you know from previous homeworks, using R and doing some of these sorts of things, if you haven't done them before, can be quite time consuming. If you've done them before, they can be done relatively quickly. So it will be important that you do your best to try to um, practice these things, which I'll try to get more exposure to us today and the review session on Thursday. Okay, so some things that you need to go ahead and make sure you have up that we were going to be using. So you need to have R up. Okay. adjust my little size here. Okay, you need to have R up. You need to have homework 4, which I sent you in an email. Homework 4 solutions, again, I sent you. The formula sheets you might want, they were sent to you at some point. You need to have your notes. Okay, so the notes, if you go on Blackboard, course content, if you haven't done it already, you can find the course notes here. Okay. You'll also need on Blackboard, if you go to code, you'll need Weibull analysis code, and you will need EANOVA regression code. Okay. And also under course content, if you go to datasets, we will need computer data. Okay. And so I'll get to that when we get to that example. Okay, so let's think back where we were a couple weeks ago. We were talking about confidence intervals, and I believe we were finishing going over the 2-sample confidence interval for means. Okay. Recall this is what the formula sheet looked like, and we had for the confidence interval for the difference between two population means. We had 3 different ways to do it. The first way, we had independent populations, or independent samples, however you want to think about it, and we assumed that the variances were equal in both populations. The second way, we still had independent samples, but we could not assume that the variances were equal. And the third way, we had dependent samples, so matched pairs design. Okay. Now, I don't believe that we got to confidence interval comparing to variances or to proportions, and this is part of the content that I'm just going to skip. Okay, we're probably just going to skip this, as well as content that would have been at the end of the course. Okay, so to get us back into things, if we look at homework 4, well, let's just go ahead and look at question 5. So we've collected data on the processing speed for 20 computers, both before and after a newly designed chip was implemented, and we want a confidence interval for the difference between the average computing speed before and after the implementation of a new chip. Okay. And we want support for our interval and the validity of the assumptions. So, first off, we can see we want a confidence interval, okay? And we want a confidence interval for the difference between the average, right? And we have a before and after, okay? So hopefully we can realize that it is a confidence interval for the difference between 2 means, 2 averages. And so that puts us here. And so we know we have 3 choices. And so really we have to get that decision from simply the wording of the question. And we have 20 computers, and we're measuring the processing speed before and after a chip is implemented. So that means each computer, we have the first set of data is the speed before, and the second set is the speed after. Okay, but each is observed on each of the 20 computers. Okay, so every observation for group 1 has a corresponding observation for group 2 before and after. That means that the samples are dependent. Okay, matched pairs design, which means we need to use this method. Okay. For the most part, I'm just going to shift more to not relying on these confidence intervals because, let's face it, uh, you could do these in practice, but I don't know why you would ever do a confidence interval by hand in today's world. Okay, you should almost always have access to a computer. R is a free program, so you can get it on any computer, and it's very, if you know the basics, it's very easy to use. Okay, so um, we know this is the third method that we want to use. It is, however, important to still understand that we need to know which method to use. Okay, right? R can't tell us which method to use. We have to know which method. So first off, let's go ahead and get the data. So computer data. Okay. I should have clicked save, not open. Oh well. Computer data. Save. Open folder. So what I'm going to do is put it on my desktop. Okay. It's called computer 1 for some reason. I'll put that as computer. Okay. So I've got the Excel file called computer saved on my desktop. And just looking at it, we can see, right, we have 20 observations. So each of these observations is the difference between the computing speed before and after the new chip was implemented. Okay. So that's maybe looking at the data set, since it's already in this format, that's another hint that we need to use that third method. So of course we would like to read this data into R. Now this is only 20 observations, so it wouldn't be the worst thing in the world to type this into R, but we don't want to do that because this could have 2,000 observations, in which case, right, that would be unrealistic to put into R. So it doesn't matter whether it's a big or small data set, we need to understand how to put it into R. So to do that, right, again, I've got the data set on my desktop. I go to my Weeble analysis code, and this final line looks like this. Okay. So I'm going to copy it. And here's something that you can do. Go to File, New Script, in R, File, New Script. And it basically just gives a text window up. So it makes it easier to modify things without modifying the original file, etc. So you can keep it as data. That's fine. So what we have here, users, of course, this is my username, right? You have to change this, but for the most part, I don't think you should have to change the rest of this on a Windows computer anyway. And then recall the Excel file was called computer. Okay? And so if we change that to computer, change that to your username, then this will read the data set in and it will call it data. Okay, again, if we wanted, maybe I'll go ahead and do that. Just, I'll call it computer. So we can, one thing you can do, you can hit Control R and it will automatically read it in. But in case you forget that, I'm just going to copy and paste it here. Okay, didn't like that. Oh, let's look. I bet it had a capital C. No, computer. Okay. Oh, okay. So this this is my work computer. Okay, so let's see. Maybe this is good anyway. If you right-click on your file and go to Pop Properties, you can see what it's called. Okay, so this is the location. Again, even though it shows single slashes, you have to put double slashes in R. So my username should be Ryan instead of StutzM. Okay, so let's see. Oops, let's see if that works. So maybe that was a good mistake anyway. So C users Ryan desktop, and then the file was called computer. And again, lowercase c. It should be case sensitive. And let's see if that works. Okay, so it looks like it worked. Just to double check that it did work, right? If I type computer, it's going to know that I'm referring to this data set, which had 20 observations, and there they are. So you can see that we read our data in properly. Okay, so that's really all that we need this code for right now, is just to read the data set in. Nova and regression, we don't need that yet. So we need the confidence interval. So if you recall, we're comparing two means. So t.test, and recall this is the third way where we have matched pairs, and once we take the difference between group 1 and group 2, remember it's just like doing the one sample case, right? And so for the one sample case, if we did t.test and we typed in what our data set was called, and recall the question asks for 80%, so we have to change that conf.level equals 0.8. Otherwise, if it was 95%, we wouldn't have to put that. And this should automatically give me now an 80% confidence interval for the difference between the two means. Okay, again, because it's the same thing as treating the differences between the two groups, taking that difference and using the one sample method. Okay, because they're dependent, right? Only because we have a dependent samples matched pair design where each observation, say, receives both treatments, right? The before and after the chip. So our general statement, right? We're 80% confident that the difference between the computing speed of a computer before and after the chip was implemented is between 0.3 and 0.6. Okay, so recalling that, so the first group should be before and the second group should be after, right? Then it looks like the first group, because both numbers are positive, has the higher mean, right? Something minus something else is all positive, so the first thing must have been bigger. And we're talking about computing speed. Okay, so I think if it's in reference to time, that means that the time, it takes longer for the first group. So the second group takes a shorter amount of time, on average between 0.3 and 0.6. I'll look back in just a second to see the units. So meaning the chip helped the computer go faster because it has a shorter time. Because again, the time is longer, more for the first group. So let's look back at it. So I guess I could have done a little better conveying that we're talking about units of time. Okay. But anyway, so let's look at the solution. It should basically be what I just said. Okay. So again, matched pairs design. For the most part, we can just kind of, don't want to say forget all about the confidence interval, but the way we would really do this is on the computer. And again, we're 80% confident that the new chip increases processing speed by 0.3 to 0.6 units. Again, units, right? I didn't give you specific units. And so the chip is better, right? It increases the speed because the entire confidence interval is positive. So since we're talking about time, assuming we're talking about time, that means that the first group takes longer. That was before the chip. So adding the chip makes it faster, less time, and which is better. Okay, well, before we get to that, we need evidence for the choice of interval. I'll kind of explain why we use the match pairs design and the validity of the assumptions. Okay, so we want the differences, right, to be normally distributed. And so how can we check that? QNorm, and what is our data set called? It's called computer. It might be QQnorm. See, uh, you know, if I don't use this stuff, I start forgetting stuff too. Okay, so we can clearly see this is not a straight line, right? We want a nice 45-degree line. We can clearly see some quadratic pattern. So it really looks like normality is violated for this. And so the results may be a little bit questionable. Um, the procedure in general is pretty robust to the assumption of normality. However, there is only 20 observations. So it would be nice if we had more observations, but I would definitely mention that the normality is violated, right? And so we can see I put it on the same scale and just grossly violated, okay? And okay, so did this a while ago. Apparently this data is actually from an exponential distribution, right? So nice curve, which is why it's curving away from the normality. And so that's pretty much exactly what we put in, right? T.test. And that's pretty much the end of it, okay? So that's something on a test. I think this is pretty much gone now, right? I can't make you show your work, any of that. If you just use the t.test function, in real life, that's how you would do it anyway. You put that into R, and it gives you the confidence interval. Okay, so as I mentioned, I think we're going to skip the two variances and skip the confidence interval for two proportions, which is the rest of chapter 8, and go right to chapter 9, which is ANOVA. Okay, so obviously if you're interested in these, you can look at the notes to gain a little more information on them, but we are not going to test on these topics. All right, so ANOVA stands for Analysis of Variance, A-N-O-V-A, okay, ANOVA. So you got to work a little bit to get the ANOVA analysis of variance, but that's what ANOVA stands for, analysis of variance. And so in the last chapter, what we just did, we did a confidence interval for the difference between two means, right? That's what our last example was, confidence interval for the difference between two means. Okay, but the first two methods of doing that, we have independent samples. So something that's common is that you may have more than just two groups, right? You may have multiple groups, okay? And so in that case, you cannot simply use a confidence interval because there are more than two groups. And that's what this analysis of variance is for. You have more than two groups. You can technically do this for two groups, but if that was the case, you could just use what we already did. And you want to compare the means. Okay, so a common thing is you have more than two treatments, and you give some independent group treatment 1, another group treatment 2, and another group treatment 3, say whatever that treatment might be. right? It doesn't necessarily have to be something medical at all. And you want to compare the means, right? Is one of these treatments superior to the other treatments? And we can see that by looking at the mean, whatever we are talking about. So uh, this analysis of variance is a special form of a hypothesis test. Okay, a hypothesis testing, probably something we should really talk more about than we do in this course. Okay, but it is a special form of a hypothesis test. Okay, so a hypothesis test, we want to compare two general hypotheses. We want to compare the null hypothesis, which is generally denoted H naught, or H sub 0, versus the alternative hypothesis denoted H sub 1. Sometimes you might see H sub A for alternative. Okay, so for the ANOVA test, we are trying to see if the means are all equal. So in this example right here, we have 4 groups, okay, and we want to see if the means are all equal for all 4 groups versus if they're not. So that is one thing. It doesn't matter what hypothesis test you're doing. The null is always going to be some statement of equality, right? See, we have the equal signs here. And the alternative is pretty much always going to be the opposite of the null. So if this is that they're all equal, the alternative would be that they're not all equal, meaning that at least one group has a different mean. So as I said, this is a special form of a hypothesis test, and we're comparing multiple means. But technically, every confidence interval that we talked about, and even the ones that we didn't, and even lots of other things, have hypothesis tests. So each one of these confidence intervals has a corresponding hypothesis test that basically gives you the kind of the same answer, if you will. So if we have a confidence interval for the mean of the group, right, we have one group, we could equivalently do a hypothesis test that the mean of our population is equal to something, right? Whatever that, it could be 0, or it could be something else that we're interested in. Now let's go back to what we were just talking about, confidence intervals, comparing the means for 2 groups. The hypothesis test version of this confidence interval is that the mean for group 1 is equal to the mean of group 2. So H naught is that mu1 is equal to mu2. The alternative is that mu1 is not equal to mu2. Okay? But as I've said, the ANOVA analysis of variance, we're specifically testing, we're specifically interested in means, and for multiple groups comparing whether the means are equal or not. And I guess I should have said we could also compare, you can do a confidence interval for the variance, you can do a hypothesis test for the variance, hypothesis test for a proportion. You can do hypothesis tests for lots of other stuff, okay? But this is really the main hypothesis test that we're going to talk about in this course, which is just we have multiple groups and we want to compare the means of those groups, okay? So null hypothesis is equality, that they're all equal. Alternative is that they're not all equal. Okay, so to do this, it is what's called an overall F-test, okay? And so there's going to be a lot of stuff. If you're interested, you can look at it. But again, I'm more focused on the practical implementation of the method than the theory behind the method, because in my opinion, even what we cover in this course, even if I went over this stuff, it's really not enough, I would say, to really understand what's going on in the background anyway. So In a way, I think shifting to a more computer-based is probably more valuable anyway. So null hypothesis, again, just trying to emphasize no difference, equality, okay? Versus the alternative is that there is a difference between the means. So the assumptions for the ANOVA. The easy way to think about it is, remember when we did a confidence interval, the method one, we assumed we had independent, right, samples, the variances are equal, okay, and that the populations are normally distributed. Basically, those assumptions are the exact same assumptions for ANOVA. The only difference is instead of having two groups, we have multiple groups. But we still want independent samples, right? Independent populations. We want normally distributed populations, and we want each group, each population to have the same variance. Okay, and those are the assumptions. Fortunately, there are no alternative methods that we're going to talk about, right? It's only this one set of assumptions. There's not multiple ways that we're going to talk about doing it. So again, I'm going to try to omit this stuff for the most part, but getting down to how the method works, we have these two quantities. We have what's called a treatment mean square, and we have what's called a residual mean square, also referred to as an error mean square. And so these are two different quantities that are estimators for the variance. Again, we said that third assumption that the variance must be equal for all of the groups. So again, this says the expected value of the treatment mean square is equal to the variance, sigma squared. This says that the expected value of the residual or error mean square is equal to the variance. Another way of saying that by definition means that these quantities are unbiased estimators for the variance. So if that is the case, and notice this says when the null is true, right? All the population means are equal, then this holds. When all the population means are not the same, it changes, okay? So this error mean square or residual mean square is always an unbiased estimator for the variance. However, the treatment mean square is only unbiased under the null when the means are equal. If the means are not equal, then this is no longer an unbiased estimator, and it tends to overestimate the variance. See, it's on average, right, the expected value, on average, it's bigger than the variance. So it's an overestimate. So what that tells you is getting to this, if the null is true, then dividing this, the treatment mean square by the residual mean square, right, just two statistics, we can see this is what the treatment mean square looks like. It's some function of the data. Again, you can look at this to see exactly what these things mean, but it's some function of the data. And the residual mean square is here. Again, is some function of the data adding the things up from the data. So those two estimators, right, on average should be the same, right? On average, they're both equal to the variance. So if you divide the two, right, you should get approximately 1. However, when the null is not true, the alternative is true, the means are different, right, then it tends to overestimate the variance, meaning when you divide the treatment mean square by the residual mean square, right, this should be approximate, like on average sigma squared, and this should on average be more than sigma squared. Thus, it doesn't matter what those two are, this should be more than 1, right, because this is now bigger than sigma squared, where this is equal to sigma squared, again, on average. So that is basically a statistic, and you can see we're calling it F. and they're kind of like the t-distribution. There is some continuous distribution called the f-distribution, and we don't need to worry about it, what its density looks like, okay? But this is now our statistic, right? And we know its specific distribution, but instead of trying to construct a confidence interval for it, we're going to instead use that statistic to do a hypothesis test. Very, very kind of similar to doing a confidence interval. So let's see. So this is a picture of what a specific F distribution looks like. Okay, the F distribution has two parameters, which are called degrees of freedom. Okay, degree of freedom 1, degree of freedom 2, 3, and 32 in this example. Okay. Um, so, um, but how do we conduct a hypothesis test, right? We're trying to compare the null hypothesis versus the alternative hypothesis. And to do that, we need what's called the probability value. I'm sure everybody's heard of it, called the p-value. This is the thing that is vastly misunderstood by the majority of people that do hypothesis testing. So one thing that I actually would like you to take away from this course is that hopefully we're going to understand the basics of hypothesis testing, but from this course you will not fully understand in depth hypothesis testing and what it means in depth. Okay. Um, in fact, if you have to do any statistical procedures in practice, one of the most common ones is to do a hypothesis test of some kind. Okay, you might be testing like in ANOVA that you have multiple groups and you want to compare all the means. You might just want to do a hypothesis test for the mean or the variance of a single group, right? But whatever it is, hypothesis testing is one of the most common procedures. And it's misunderstood by just about everybody who does it. Even people that should know better, such as people with master's degrees in statistics, there are a number of these individuals that don't understand hypothesis testing as well as they should, or think that they do. So I do want to ingrain into that is that just from this course alone, you do not fully understand hypothesis testing, and nor do just about everybody that you encounter. Okay, but with that being said, we use that F statistic, right? The treatment mean square divided by the error mean square. This is what allows us to calculate a p-value. Okay, and so the definition of a p-value, it is the probability, it's probably here somewhere, it's the probability of observing our results or even more extreme results given that the null hypothesis is true. So the probability of observing our results or even more extreme results given that the null hypothesis is true. This is one of the things that confuses a lot of people. I would say the reason why hypothesis testing is so confusing is because it does not give us the answer that we want. Okay? What we want it to do is tell us the truth. Okay? That's just inherently, that's the most logical thing. We want to do this procedure and we want it to tell us the answer. But unfortunately in statistics will never tell us the answer. And that's what makes it so easy to misconstrue what this is actually telling us. Okay? Okay, so the p-value. As it's saying here, we're going to calculate it. Again, it's the probability of observing our results or even more extreme results given that the null hypothesis is true. So if that value is small, then that means there is a very small probability, right? Small p-value, small probability of observing our results or even more extreme results, given that the null hypothesis is true. Okay, so that means that the smaller p-value, smaller probability of this happening under the null hypothesis. So it is a way of having more evidence against the null hypothesis, right? Smaller probability of observing our results under the null hypothesis makes it less likely in a way that the null hypothesis is true, right? Because we have a low probability of observing what we did observe, what we truly observed, if in fact the null hypothesis was true. Okay, but again, small p-value, right? And as with everything else, well, how small, excuse me, how small is too small? Um, well, if we go back to confidence intervals, remember there was this pesky alpha, right? Why did we bother with this alpha? It seems like, right, I know alpha's over here, but it seemed like there could have been an easier way of just doing a 95% confidence interval without having to know that alpha was 0.05. Okay, one of the reasons that we do this is that confidence intervals are very connected to hypothesis tests. Like I said, each one of these confidence intervals has a corresponding hypothesis test, even though we didn't discuss it in this course. And that alpha is one of the things that connects the confidence interval to the hypothesis test. So for example, if I do a 95% confidence interval, we'll just take this for an example. Maybe I'm testing that the mean is equal to something, right? What it is whatever would be important in that example. If I wanted a 95% confidence interval, that would imply that alpha was 0.05, okay? Which that becomes important if we want to look at the corresponding hypothesis test. I would need to know that alpha was 0.05 because that would allow me to get the same answer as the confidence interval. So alpha is actually what's called the significance level, okay? Significance level. Let's see if I can find it here. Okay, significance level, okay? Alpha is called the significance level. So having an alpha of 0.05 is, you can think about it as kind of like doing a 95% confidence interval, right? It's equivalent to a 95% confidence interval. Okay, now that's an easy way to think about it. Okay, so how small is too small? Well, if I want to think about it like a 95% confidence interval kind of, then I have alpha's 0.05, and if the p-value is less than or equal to alpha, that's too small, okay? So if the p-value is less than or equal to alpha, you reject the null hypothesis. Okay, looking for that in words, hopefully. Okay, the p-value is less than or equal to alpha, reject the null hypothesis. Not that it should matter in most cases, but technically this should be less than or equal to and not less than. Okay, this is a typo. Okay, so if the p-value, right, the probability of observing our results or even more extreme results, given that the null hypothesis is true, is less than or equal to alpha, right, 0.05, then I reject the null hypothesis. Okay. And so what happens when I reject the null hypothesis? When you reject the null hypothesis, you have evidence that the alternative hypothesis is true. Now, I want you to remember back to these confidence intervals, right? Regardless of which confidence interval, there was a couple different ways that I could come to a conclusion, right? Sometimes I had evidence, but what happened when, say, take this for example, mu1 minus mu2. Remember when 0 was included in that confidence interval, I did not have evidence that one mean was bigger than the other, right? I didn't have evidence that the first mean was bigger, and I didn't have evidence that the second mean was bigger. So it's the same thing with hypothesis testing. You can either have evidence or not. So if you reject the null hypothesis, that is when you have evidence of the alternative hypothesis. Okay? So that's kind of equivalent to just taking this for an example. Remember, when the entire confidence interval does not include 0, that's when you have evidence that one of these means must be bigger. Okay? So if I reject the null hypothesis, I have evidence that the alternative hypothesis is true. And so let's just recall in ANOVA what we're testing. We're testing that the means of all groups are equal. Okay. So here's the general one, right? T groups, right? However many that is, we have multiple groups, and we're testing whether the means for all of the groups are equal or not. So if my p-value is less than, almost always you'll see alpha's 0.05, kind of like a confidence interval. It's just what's generally done, and it has a lot to do with, I would say, in some ways, it has something to do with people kind of trying to be consistent. But more so than that, I think there's also a lack of understanding that goes into these hypothesis tests, because more realistically, choosing the significance level to be smaller or larger makes sense depending on the application, but I really don't want to get into that. Okay, so if my alpha, so my p-value is less than or equal to alpha, say 0.05, then that's when I reject the null hypothesis. I reject that the means of all the groups are equal. And I have evidence that they're not all equal, okay? That is when I have evidence. When you have the p-value less than or equal to alpha, you have evidence that the means are not all equal. You have evidence of the alternatives, right? In general, the alternative is whatever. Could be lots of other things, okay? But for right now, we're doing specifically an ANOVA F test. And the alternative is the means are not all equal. Okay, so what happens when the p-value is not less than or equal to alpha, right? Say alpha, the significance level is 0.05, kind of like doing a 95% confidence interval. What happens when you get a p-value of 0.06 or maybe 0.3, right, or 0.8, right? You can get p-value, recall probability value has to be between 0 and 1. It is a probability value, so it has to be between 0 and 1. So in order to get one above the significance level, it could be anything from 0.06 to 0.9, etc. In that case, the statement is we fail to reject the null hypothesis. Let's see if that's written somewhere, but that is the terminology that I'd really like for you to try to remember. Excuse me, is that we fail to reject the null hypothesis. Okay, reject the null. I don't know if he puts it here. Okay, so reject the null. If the p-value is greater than alpha, fail to reject the null. Okay, fail to reject the null if the p-value is greater than alpha. That is the case where we do not have evidence. That is kind of like, think about comparing two means for a confidence interval. That is like when the confidence interval includes 0. It's not that we're saying that the means are the same, right? When we did a confidence interval comparing two means, we didn't say if the confidence interval included 0 that the means are equal, right? That's not what we said. We said that we don't have evidence that they're different. It's the same thing with hypothesis testing. When we fail to reject this null, right, it's not that we're saying, right, fail to reject, why don't we just say accept, right? That's something that why not say accept? It's because we're not accepting it. It's not saying that we have evidence that the means are all equal. It's just saying that we don't have evidence that they're not all equal. Again, exactly like that confidence interval including 0. It's not saying that they are equal. It's saying that we don't have evidence that they're different. Same thing here. When we fail to reject the null, we're not accepting it. We're just saying that we don't have evidence of this. So we either, when the p-value is small, right, p-value less than alpha, we reject the null hypothesis and have evidence of this. When the p-value is large, right, greater than alpha, we fail to reject this, so we don't have evidence of the alternative. So that's basically, we either have evidence that the alternative is true or we don't. We never have evidence that the null is true. Okay. And I think it's about time to see an example. Okay, let's see an example. Okay, let's go to our ANOVA and regression code, which you hopefully have up. And we need to copy this line, attach iris, and put it into R. Okay, now let's go ahead and type iris. And so this attach iris, this is a built-in data set in R, but we just have to put this line so that R knows that we want to work with it. Okay, so the iris data set, I don't think we've seen it yet. It contains the sepal is some part of a flower, I guess. It contains the sepal length, the sepal width, the petal length, and the petal width. Okay, and these 4 variables, right? Two length variables and 2 width variables are measured on 3 different species of flowers. Okay, there's a Setosa flower, there's a versicolor flower, and there's a virginica flower. Okay, so in this example, we have what might be of interest to us is maybe one of these variables specifically. Let's see in my example what we do. Sepal width. Okay, sepal width. So with this data set, what the researcher might be interested in is, does the sepal width of a flower vary depending on the species? Okay, and one way to answer that, right? So that's kind of going into research. That's the question that the person might have is, right, does the sepal width vary depending on the species of flower? And now you have to figure out, well, how do I answer that question? Well, ANOVA is a very good way to answer that question, okay, because we can think about the 3 species of flowers, Setosa, versicolor, and virginica, as groups, right, 3 groups, and we want to compare the mean sepal width for each of the 3 groups. So again, we have 3 groups, so we can't do just a confidence interval. We need to use the ANOVA procedure, okay? And so that we can answer that question with an ANOVA F-test. Okay, so we'll just go ahead and assume that we're using our generic kind of 95% confidence interval, thinking about it like that, and an alpha, a significance level of 0.05. That's what we want to use to make our decision. So right here I have ANOVA. This LM stands for linear model, and I want to compare the sepal width, right, my variable, across species, right? So these are my groups, right? Sepal width across species. And again, right, sepal width and species contains my 3 different groups, my 3 labels. Excuse me. All right, so I typed that in and it gives us an analysis of variance table. Okay. Usually in the course I go a little bit more in depth into what each of these things kind of means and just kind of figuring it out by hand. but we're going to skip that. But what I do want to point out, this mean square, the species mean square, this value right here is the treatment mean square. This value right here is the residual mean square, or the error mean square. Okay, right? So these are the two quantities that get divided, right? This divided by this gives us the F value. Okay, but realistically, we just want to we can summarize all of this in our p-value. Okay, unfortunately, R gives it to us like this: probability basically greater than F. Okay, this is the p-value. Okay, very important to understand. That's the p-value, or you're going to be very confused, right? This is the p-value right here. And this 2.2 e to the negative 16th, recall, this is a very crappy way of putting 2.2 times 10 to the negative 16th. Okay, so right, 16 zeros or 15 whatever, and a 2. So something extremely close to 0, right? Very, very small p-value. Okay, so thus the p-value, right, 0.000, a bunch of zeros, 2, is less than or equal to 0.05, right, alpha, our significance level. And so looking back, what do we do, right? P-value is less than 0.05, right? 2.2 times 10 to the negative 16th, something very small, is less than 0.05, so we reject the null, right? And that is the decision where we have evidence of the alternative hypothesis. So again, let's go ahead and just, maybe I can type it in. So in this case, the null hypothesis, I'll just put H0, well, H sub 0, I don't know. That's fine. The null hypothesis is that the means of all three, here, the mean sepal width, that's the variable that we're interested in. The mean sepal widths of all three species of flowers are the same, and the alternative hypothesis was right, at least one mean sepal width is different. Okay, those are the two hypotheses in the example that we're dealing with. Okay, so this says, right, mu1 is equal to mu2 is equal to mu3 versus, right, at least one is different. And the mean that we're talking about is the mean sepal width for these three species of flowers, right? We can write mu1 is the mean sepal width of a setosa flower, mu2 is the mean sepal width of a versicolor flower, and mu3 is the mean sepal width of a virginica flower. Okay, so we got a very small p-value, which, as we just saw, right, reject the null hypothesis. So we're rejecting that the mean sepal widths are all the same, and we have evidence that at least one mean sepal width is different, right? One of these species of flowers must have a smaller or larger sepal width than the other two, right? It could be that they're all three different, right? But at least one is different. So our conclusion, this is a very standard way to write it up. At the 0.05 level of significance, we have evidence that the mean sepal width differs across flower species. Okay, that's our conclusion, right? Small p-value, and here, because the p-value, right, and I'll put it like this, right, approximately 0, right, is less than 0.05. right? Our p-value, maybe I'll put it like this. Just trying to make it easier to understand. Okay, we have evidence at this level of significance that the means are different across the species of flower, right? The mean sepal widths are different across the flower species because the p-value is less than alpha. And again, the p-value the p-value, when we did our ANOVA of this, our p-value was right here, p-value, and this is basically 0, right? 10 to the negative 16th, so something very small, almost 0, is less than 0.05. And again, p-value, I know I say it a lot, the probability of observing our results, or even more extreme results, given that the null hypothesis is true, is less than 0.05, right? Less than 5% probability of observing our results given that the null hypothesis is true. And if you really take a minute to think about that statement, it's one of the reasons why hypothesis testing doesn't give us the answer that we want it to give us. But this is the way we state it. Okay. So the alternative conclusion, I'll put if, right, we got a p-value greater than 0.05, say 0.08, right? Can be anything greater than 0.05, right? Big if here, right? I want to put it in both ways. If we got a p-value greater than 0.05, then, okay, we have a different conclusion, okay? At the 0.05 level of significance, right? Well, here, I'll just modify this. Oops. At the 0.05 level of significance, we do not have evidence that the mean sepal widths differ across flower species because the p-value, in this case, right, 0.08, is greater than 0.05. Okay, again, assuming that this number here was, say, 0.08, then that would say at this significance level, we do not have evidence that the mean sepal widths differ across the species, right? That the means are not different across species because the p-value is greater than 0.05. Now notice we did not say that we have evidence that the means are all the same. Okay? It's just that we don't have enough evidence to say that they're different. Okay, maybe they're different, maybe they're not, but our test was inconclusive. Okay, so again, large p-value is basically indecision, right? We don't have necessarily a nice conclusive decision, whereas when we have a p-value less than our significance level, we have a decision, right? It doesn't mean it's the right decision, but it is at least a decision based on our test. Okay, so however, in practice, what might we be thinking? We're probably thinking, right, that if we had to make a decision, then maybe if we have this scenario here, we're probably maybe going to assume that maybe they are equal or similar. Okay, that's probably what the practitioner is going to do. Okay, but because it's certainly not suggesting that they're different, right? However, specifically, it is saying that we just don't have evidence that they're different. Okay, not necessarily that they are in fact equal. Whereas this one is, yes, we have a nice, finite, conclusive decision, and we do believe that they're different. Okay, so if this is the case, we're pretty much done, right? We're saying, well, there's no evidence that they're different, right? So there's nothing left to do. For this one, We're saying that they're different. However, we're still probably wondering, that doesn't tell us which one is maybe is the biggest, which one is the smallest, etc. It just says that there's a difference. So if we do find a difference, if we reject the null and we have evidence of the alternative, then we can go further. We can say, okay, can we determine a ordering of these means, right? Because a lot of times we might have 3 groups, or maybe we have 4 or more groups, okay? But before we go into that, for either decision, we want to check our assumptions, okay? Verify what are our assumptions. Well, we assume that we have independent groups, okay? So just assuming that there's not some systematic pattern um, of the way these flowers are, right? It should just be we have some Setosa flowers, some versicolor flowers, and some virginica flowers. So hopefully it's safe to assume that the groups are independent. Okay, but what we want is we want the petal width of Setosa flowers to be normally distributed. Sorry, sepal width. The sepal width of virginica flowers and the sepal width of versicolor flowers to all have normal distributions. So we want 3 normal distributions here because we have 3 species of flowers. That's the second assumption. Let's see if we can verify that. Okay. So this line of code here, again, ANOVA and regression, QQ norm, right? Hence that we're doing a QQ plot or for normality, right? Checking the normal assumption. And so what this is doing is checking that the sepal width for Setosa flowers, okay? And recall we want a nice 45-degree line, and that looks fairly good, okay? It looks like pretty much everything looks great except maybe this one outlying point. So overall looks pretty good. Now, if you look at the plot, you may kind of be questioning kind of this step looking thing, right? We got lots of values that are in line here. This is not a bad thing. The reason that we have these kind of straight lines here is because the measurements taken are not very detailed, right? We can see they only go to 1 decimal place. So that means that, right, we have lots of flowers that have the exact same sepal widths because they didn't measure them very, to very many decimal places. Okay, that's the only reason. So it's kind of like having they're measured discretely, right? There's only so many values of sepal widths because they didn't measure them very accurately, which is why we get this. Okay, so that's not a bad thing. If we say measured this to hundredths places, that would eradicate this step function looking thing. You get more of a smoother line. Okay, so that's not bad. Okay, I'm just going to kill that. But so that says that the sepal widths for the Setosa flowers are fine, but we still need to see for virginica flowers, are they also normally distributed in their sepal widths? And that's what we do. All we had to do was modify species equal virginica. And now we get something, again, a step function, but right, it's following that line pretty good. Okay, that looks pretty good. And the other one was versicolor. Versicolor. Again, looks pretty good. Right, so that would be 3 graphs, 3 different QQ plots, 1 for each species of flower, right? And each one of those looked like it had a fairly straight 45-degree line. And so the normality looks good for each of these 3 populations. So we have independent groups. They all are normally distributed. And the last assumption that we have to verify, recall we assume that the variances are equal for all 3 groups. So one way to just very quickly get an idea of if that is true is with a side-by-side box plot, which is in that code, ANOVA regression code box plot, and I want to compare my sepal widths across species. And this is what we get. So we can see each box plot corresponds to one of the different species of flowers, and all we're looking for here is the rough shape of the box. We want roughly the shape of each box to be the same. Doesn't matter where it is in the Y dimension, it only matters the shape. So if we kind of push this box up a little bit, it would look very similar to this. And of course, this does have one outlying observation, but if we kind of think about pushing either of these two boxes up to this one, it also looks pretty similar. So based on this, it looks like the variances of the sepal width are pretty similar across the three species of flower. Again, because the boxes, regardless of where they are on the y-axis, are pretty similar in shape. Now, this is the most important assumption in ANOVA. It is not robust to the variances being different. And if you recall, the t-test wasn't either. Or the confidence interval that we did comparing two means was also not robust to the assumption of equal variances. Okay, but in this case, I would say that looks good. Okay, so I would say that all of our assumptions look good. Independent random samples, and of course, as with everything, we want random sample. Each group is normally distributed, and the population variances are equal. Okay, so all of our assumptions seem valid. Okay, as I said before, this is what we actually got, right? A very small p-value. So we have evidence of the alternative that at least one mean is different. So we can go further than that to try to discover which means or which mean is different. So to do that, we use what's called a Tukey pairwise comparisons procedure. Tukey pairwise comparisons, okay? And technically, we're doing confidence intervals. And so what we're doing is we've detected that at least one of these means is different. So what we're going to do is we're going to take each pair of groups and we're going to do a confidence interval, kind of like we did here. I got rid of it on accident, I guess. Right, a confidence interval. And we're going to take each pair of groups, right? So for example, when we have three groups, we can think about doing a confidence interval for the first group minus the second group, first group minus the third group, and second group minus the third group, right? Comparing each possible pair of the three groups and doing a confidence interval for each one. And of course, the confidence interval, right, we have these assumptions that the variances are equal, they're independent, etc. But the confidence interval looks a little bit different. It looks a little bit different because when we do lots of comparisons, what this Tukey procedure does is that ensures that overall we are, if what we're interested in is 95%, overall we are 95% confident in all of our decisions. Okay, recall just if the probability of A is 95% and the probability of B is 95%, the probability of A and B is less than 95%. So if you do a bunch of confidence intervals and each one is 95% confidence, then overall you're less than 95% confident that you got all of them right. So what this Tukey procedure does is it basically sets the confidence interval higher for each individual confidence interval so that overall we are 95% or whatever confidence we want, confident of all of our decisions. Okay, so it's going to do a confidence interval for each possible pair of means. Okay, the rest of that is not as important. Okay, and so to do that, we do this line here, And if I look, a lot of this stuff doesn't need to be modified. We can see confidence level 95%. And I can see, again, I'm dealing with sepal width across species. Okay, most of this other stuff wouldn't ever need to be modified. So that's what I want to do. Again, I have evidence, right? We rejected the null. We have evidence that the means are different. So now we want to look to see if we can detect where those differences are. So for our first confidence interval, we are comparing versicolor and setosa species, but of course what we're comparing is their sepal widths, right? Don't confuse what we're comparing. We're comparing the sepal widths for these different species. So this first column you can ignore, this last column you could ignore. This is the lower bound of the confidence interval, this is the upper bound of the confidence interval. So for basically the mean sepal width for versicolor minus the mean sepal width for setosa, the confidence interval is between -0.8 and -0.5. So just right back to that confidence interval chapter, that confidence interval is completely negative, so we should have evidence, right, that one of the means is different, but it's negative, which means that the second group must have had the higher mean, right? So this first confidence interval tells us, this first confidence interval, again, this was hypothetical, this wasn't this case, this is the real case. So doing Tukey, the first one tells us that versicolor, right, the mean versicolor is less than the mean setosa, right, for sepal width. And this is what the procedure that I would do is kind of check each one and say what it tells you and then summarize them all. So let's go down to the second one. Again, ignore. Now we're comparing two more, but now it's again completely negative, right? Negative to negative, which means that this one, the second group was against setosa, has a higher mean than virginica. So virginica is less than setosa. The last one we can see is positive to positive, right? So the mean for this first one, virginica, is greater than versicolor. So all three confidence intervals did not include 0, we can see here, which means we are going to be able to perfectly order all three groups, okay? It very commonly, one of these confidence intervals might include 0, which means we're say maybe going to be able to determine the highest or the lowest, but we can't perfectly order all three. That's what would happen if one of these confidence intervals included 0. But none of them include 0, so we're going to be able to perfectly order all three. So let's summarize. Well, we can see setosa is greater than virginica, and setosa is greater than versicolor. So setosa has the highest mean sepal width, okay, followed by, so again, we can order all of them. There's no question marks here, right? No confidence intervals that included 0. And virginica, right? Virginica is greater than versicolor, but of course less than setosa, followed by virginica, and then versicolor has the lowest mean sepal width. Okay, and so we can determine that based on these intervals. Let's just assume, right, if we had these two, that would tell us, right, from those two that setosa has the highest mean, but if, say, this last one included 0, maybe this was negative 0.04 to 0.36, that would tell us that we cannot determine a difference between virginica and versicolor, but based on the first two that we know setosa has the highest mean. So again, it just depends which confidence intervals include 0 and which don't. Okay, so that's the basic procedure for ANOVA. If we want to test whether the means are all equal or not, If we don't have evidence that they're different, right? If we get a high p-value greater than the significance level, then we don't have evidence of the alternative that the means are different. But if we get a small p-value, then we do have evidence that the means are different. That's when we want to use this two-key procedure to compare each pair of groups and write out some statement of exactly the ordering that we can determine. Like this, we can sometimes determine the entire ordering, sometimes we cannot. Okay, so that's pretty much everything that's going to be on the test, but again, I am going to try to review stuff for the next lecture and really try to pin down a little bit better what you might be able to expect for the test, because it's certainly going to be a lot different than any other test I've given in previous courses. Okay. All right. See you for the next one.